Okay, the topic today we are going to deal with is application of Biot-Savart's law, the second one. It is to find the magnetic field at a point due to a current carrying coil or a loop. See guys, previously we dealt with the magnetic field at a point due to a straight conductor, right? Now we are going to rotate it or make it into a curved coil or coil as it is. So we will consider a coil. We're drawing like this. So magnetic field due to this coil I have to find at a point P, say. Right, clear? Now let this point be at a distance x from the center of the coil. Right, this is center. Let it be O. Right, now just to find the magnetic field at P, right, I will usually consider a part of the coil. Just like the previous case, we considered a small element dl. Here also I have to consider a small element. Let this be an dl with A and B. The length of this element is dl. Let the current be flowing through this coil in this direction. So dl's direction is also in the direction of the current, or here the current's direction will be tangential, right? So dl's direction will be also tangential like this. Clear? Right, this is the direction of dl, guys. Clear? Now let the radius of this coil be, it's a coil, it's a circular. So why have I drawn it as in the form oval shape? Because I have kept this way you will see it as a circle, this way you will see it as an oval shape. Clear? So side view of it. Clear on? Let the radius be A. So what will be this distance be? That is the distance of the element from the point from where you want to find the magnetic field. Let that be R. Now R will be equal to root of A square plus X square. Right. Now guys, the previous section, that is the magnetic field at a point due to a straight conductor derivation, I have given you two derivation, right? Both the derivations has not been mentioned in your NCERT textbook, but it is usually asked in examination because the examination point of view question. So you can provide the derivation by either method. Both of them are correct. Clear? Okay, let's move on. Now we are considering due to this element dl, that is the length between A and B, there is a magnetic field at P. Let that magnetic field be small dB. Okay, so if you have to find the entire magnetic field, you have to integrate it. This and all you are taught previously. Now what is the angle? Some of the parameters you have to find, right? Now you remember the Biot-Savart's law, that is dB is equal to nu 0 by 4 pi I dl sine theta by r square, where r is this one. That much you know. So there is a sine theta, right? What is a theta? Angle made by the element with the r, right? What is the angle made between dl and r? It is not visible by this figure, right? What is, see, if this is a ring like this, if this is a ring, this is the dl, right? Tangential like this, right? So I'll hold it like this. So this is your dl, this direction, and which is the direction of your point? You are taking the point like this, right? So what is the angle between them? It is 90 degree. I'm repeating it again. So this is your bangle or ring or whatever round surface you are having. If you are having, you can take it, right? Tangential is like this, right? Now along with this tangential, you are considering a point P, right? It is quite different distance from this angle. What is the angle here? It is 90 degree, right? So theta is equal to 90 degree. Clear? See, if this is front view, the point is from here, like this, right? Whereas the tangential is like this, so the angle is 90 degree, like that. Right, so you're having theta is 90 degree, so 9 sine 90 degree is 1. Right, this and all should be registered in your mind itself. So what is the magnetic field at P due to, or according to Biot-Savart's law? That is dB is equal to mu 0 by 4 pi I dl sine 90 goes off, it becomes 1, that is r square. If you want, you can write sine 90 degree here. Right, so it becomes mu 0 by 4 pi I dl by r square. Now see, you have to find, see, I consider just like the previous your straight conductor, we have to consider element above as well as below, right? Then only you understand the entire thing. This is a positive side, second this is negative side, like that I taught you in the case of conductor, right? Similarly, if I consider an element here, similarly I have to consider another element here also. Why, I will tell you. Now guys, see, this dB or this element dl is in this direction, right? Similarly, the r, this is actually r vector, right, in vector form, because magnetic field is in vector form. So this direction dl perpendicular to the r, perpendicular to there is r. So in which direction will be b, dbv? How will you take your palm, take your dl, right, dl's direction, take your fingers, turn it in the direction of r, right? This is the direction of r. Your finger or thumb gives you the direction of b, right? So this is the direction of db, clear, due to this element ab. I hope this much is clear. This is the direction of db, right, due to the above element. Similarly, do I have an element, so let's take this is to another element a dash, b dash. Which direction the current element will be? The current is in this direction, right here. So the element will be in this direction, dl's direction, dl vector. And see, if I take r, it will be from here. I'm drawing it very light, guys, right? So it will be in this direction. Turn your fingers just like earlier, guys. Okay, keep your fingers in GL direction. You have to turn in this direction, right? In this direction your R is there. In which direction? Like this. You have to turn like this, right? So I'm writing the fingers like this. See, like this. Which direction the thumb is? I'm going to bring it towards the video. See, in this direction, right? So my dB is in this direction. Right, pause the video, try to understand it, guys, how it has been made. Clear? Now let this angle be theta. Right, so this angle is also theta. Right, then try to find this angle. You will find this angle is also theta, this angle is also theta. See, this is a small element which is making with this point P. Similarly, small elements dB is making an angle theta. See how you have had to find. I can just say this angle is 90. Similarly, this angle is 90. Let's find how you are going to find this angle. This is angle theta and this angle theta. You guys have to find it by yourself. How? Right? If this angle is theta and this is also theta, can't I divide dB into two components? Yes, this will become dB cos theta. This becomes dB cos theta. Right. Similarly, there is a sin theta section, right? In which direction it will be? Right. Both of them will be dB sin theta and dB sin theta, right? Both sections dB sin theta will be in the same direction. So cos of the dB doesn't provide because they both cancel out. Only dB sin theta provides a magnetic field. So the net magnetic field, if I write B, is equal to sum of dB sin theta. Clear? That is equal to, this P is actually integral dB, right? Right. So I have to write it as integral 0 mu 0 by 4 pi I dl by r squared, because that is dB, r squared. Then sin theta. Sin theta, it is along x or x-axis, or you can say that is along the axis. Right. Clear? Now here I'm going to write, let's move on to this section. So integral mu 0 by 4 pi I dl divided by what is r square? This one, right? So a square plus x squared, root raised to square goes off, right? And what is sin theta from this triangle? It is, see, a divided by hypotenuse, right? So a divided by, it is a square plus x squared. In place of root, I am writing it as raised to 1 by 2, right? Now here, guys, how many values are constant? Mu 0 by 4 pi constant, current is constant, a square plus x squared, these three parameters are constant, right? So I will write it outside. So it is mu 0 by 4 pi I into a, right? Loop's radius is not going to change. Now what is a square plus x square into a square plus x square raised to 1 by 2? X into x raised to 1 by 2 is x raised to 1 plus 1 by 2, that is x raised to 3 by 2, right? So here I can write it as integral, or here I write it as a square plus x square raised to 3 by 2, and there is just a dl inside the what? Integration part, right? So what is integration of dl? That is what happens if I take the summation of length. It is the entire circle, right? So I'm going to just write this section in okay, I'll write here. It's a mu 0 by 4 pi, right? It is I into a square plus x square raised to 3 by 2. What is the entire circumference? It becomes 2 pi a, right? Clear? Now I can write this one as mu 0 by 4 pi 2 pi, I will write here I a squared by a squared plus x squared raised to 3 by 2, right? Right, let's just keep this equation here, guys. I have a modification to be done to this equation later on again. Now out of this 2 pi and 4 pi I can cancel it out, so this becomes what? Mu 0 by 2, then there is just an I a square, then into the denominator a squared x squared raised to 3 by 2. That is your what? B's formula. Due to magnetic field at a point due to a circular current carrying loop, right? This you have to by heart it, guys. It's very easy if you understand the logic of it. Now I told you I have to modify this one. Okay, that's just to introduce a term called magnetic dipole moment, which you will later on learn, yet I wanted to introduce here itself, right? Now here, see, there is a pi a square, right? What is pi a square? Pi into what? Square of the radius, that is the area of the circle or the circular loop, right? So I can write this equation in the form of mu 0 by 4 pi, right? Pi into a square goes, right? So it is 2 into I into area divided by a square plus x square raised to 3 by 2, right? Now here, see, this is for one turn, this is also for only one loop, right? What happens? There are multiple loops, that becomes here n. Don't write n just like as I have written here. You have to separately write the entire equation, then multiply with n. So if there are n loops, you have to multiply with n number. Here also, this is for a single loop, right? So what happens if there are number of loops? It becomes n into, right? Now we require this term. That's why I tell you. What is n into I into a? See, n into current into area of a circle or a coil. This is known as magnetic dipole moment. You will later on learn this what it is, but just know that it is magnetic dipole moment, and it is represented by capital M. What? Capital M. So I can write the previous equation, that is magnetic field at a point due to current carrying loop, can be also written as mu 0 by 4 pi IAN goes off as 2m divided by a square plus x square raised to 3 by 2, or I can write it 2 cancels, so it becomes mu 0 m by 2 pi a square plus x square raised to 3 by 2. There is a representation of magnetic field at a point due to a circular coil loop in terms of magnetic dipole moment, right? Later on you will learn what is magnetic dipole moment. I just wanted to introduce here itself. Clear? So n number of turns, multiply with n. Now there is just one more case here. What happens if this point I am considering at the center? That is, what is a magnetic field of a coil at its center? When you consider center, this x goes off, x undavilla. Anganeyanengil, what happens to this equation, guys? B is equal to mu 0 by 2 I a squared. Let's not take n, you will later on take it as n, right? A squared, then a x square goes off, right? So a square raised to 3 by 2. So 2 cancels off. Denominator there will be mu 0 by 2 I a square. Let's make it as a division here. divided by A cube. Right, so 1A goes off, so you will get the equation of mu 0 I by 2A. Very important equation. This is the magnetic field at a point or at the center of a current carrying loop. That is mu 0 I by 2A, where A is the radius of the circular loop. Clear?